So, good afternoon, everyone. Welcome to our presentation. Today, I'm glad to present our work at SIGGRAPH 2011. So, the input of our problem is an image of a transparent object. And what we want is to output a composite image where the transparent object is pasted onto a new background with proper visual effect. Conventional mapping algorithms assume the foreground object to be opaque, and so they do not work for transparent objects. So we propose to solve the mapping problem of transparent and refractive objects from a single image, and we believe we are the first one to make it practical. Our contributions come along with an appearance-based model called attenuation-refraction method, or ARM, and the using of interactive techniques to extract our model. After extracting our model, we can generate complex composite effects easily without any 3D information. Before I go into the details, let us see how do we humans perceive a transparent object. Actually, humans perceive transparent object by three main factors: specular reflection or specularities, color attenuation, and refractive deformation. Without these three factors, humans can hardly perceive a transparent object. For example, you may have experienced that almost hit on a planar glass door. So now the question is, how do we make use of these observations to solve our problem? The top is the conventional mapping equation for opaque object. So mapping is a well-known ill-posed problem, and it requires user interaction to help solving the problem. And now we are going to make it even more ill-posed. Based on the observation, we extend the conventional mapping equation for opaque object into a more general equation which can handle transparent and refractive objects. We replace the notation I to C. The foreground is represented by specular highlight, and we replace the notation as S. We introduce beta for color attenuation and G for refractive deformation. So alpha, beta, G are part of the model to be extracted. We define M, which is the object silhouette, and it is also the processing region. So these four components, M, alpha, beta, and G, are collectively known as our attenuation-refraction match, or ARM. And the ARM model for the lion is shown here. So the problem is more ill-posed, so an interactive approach is expected. And before I tell you how do we extract our ARM components, I would like to let you know the assumption that we have made for our approach. We assume the white specularities as the foreground, and they are caused by illumination outside the scene. So we have this assumption because if the illumination is caused inside the scene, or let's say behind the object, then even the user may not be able to distinguish whether these highlight pixels are directly from the illumination or reflected by the transparent object. Second, we assume the color attenuation is piecewise smooth. This simplifies the computation of our beta. And only the visible part of the background is deformed by the object. So we make this assumption so that we can apply user markup on the background to estimate our refractive deformation G. So here I want to show you an overview of our interactive ARM extraction. First, we'll extract the object silhouette M, which defines the processing region. Then we can estimate the foreground contribution alpha. After that, we estimate the color attenuation beta and also the refractive deformation G. With the extracted ARM model, we can extract the original transparent object and put it onto a new background. We use interactive segmentation technique, lazy stepping, to extract the silhouette. Inside the silhouette, we can also segment different refractive regions easily. To extract the foreground contribution alpha, we need tri-map. And our definite foreground region will be those white highlight pixels. To avoid tedious user marking, we propose to compute the tri-map automatically by simple thresholding. User can refine the tri-map by some simple strokes. With the tri-map, we can solve for the alpha map, and the alpha map can also be edited if needed. To extract beta, user only needs to mark up texture region outside and inside the object by simple strokes. For better result, the foreground contribution will be removed before the computation. A simple Bayesian optimization is solved to obtain the result. Since we only have a single image, it's impossible to extract the real refractive deformation. Instead, we target on plausible effects. And the key reason for this approach being successful is because our human visual system tolerates the inaccuracies of refractive phenomena. And I will demonstrate this fact to you shortly. The refractive deformation is represented by a 2D warping function, and we pick frame-pace splice function to represent this 2D warping function. We pick frame-pace splice simply because of its computation efficiency. So user will specify the strokes in pairs to specify the warping. The strokes can be specified in two ways. We can follow the foreground shape of the object or follow the shape of the deformed background texture. For the foreground cue, there are three basic effects: low reflection, convergency, or divergency. And they can be achieved by simple strokes. In this slide, you can find that human is actually insensitive to the correctness of the refractive deformation. 6 images here, only 1 is real. The other 5 are synthesized by our method. Can you spot the real one? Well, maybe let me give you 10 seconds for you to find out the answer. Okay, here's the third one. I hope you picked the correct one. So here, I'd like to show you a video of the markup to give you some feelings on the actual interaction. So we use interactive segmentation technique to extract the object silhouette. So automatic tri-map with simple user refinement. The alpha matte can also be edited if you want. To extract beta, user mark up similar texture regions inside and outside the object. To extract the refractive deformation G, we can follow the foreground shape of the object by the foreground cue. Or you can use the background cue by following the deformed background texture. So after extracting the arm model, we can composite the transparent object onto a new background. So the next question is, can we achieve better visual effects? Well, we need to do more to achieve visual realism. We have to simulate the Fresnel effect, the caustic shadow. We can also simulate scene depth and do compound composite. And these effects can be achieved with our arm model easily. So when you look at a transparent object, its boundary looks like opaque. It's because the light at the boundary region is glanced off and cannot enter your eyes. So it looks like opaque to you. And this effect is called the Fresnel effect. Without the Fresnel effect, the transparent object doesn't look solid. So without any 3D model, we propose to solve it based on the image information. And we term our method Poisson boundary blending. The idea is very simple. We try to maintain the image structure along the boundary from the input image. And then we transfer the color tone from the composite image. It's done by solving the Poisson equation with the boundary condition from the composite image. So the object in the composite image maintains the image structure from the input. Meanwhile, it has the color tone from the new background. And the result looks much nicer with the boundary Fresnel effect. So caustic shadow occurs when light rays redistribute after passing through the transparent object. For example, in the white image, the light convergency will make the projected shadow brighter. Or on the other hand, the light divergency makes the area dimmer. So ray tracing or photon mapping is common practice to generate the caustic shadow, but it requires the geometric model. And in our case, we only have a single image. So again, without any 3D information, our idea is to simulate the light redistribution from the background to the object. And it can be done by histogram binning. So there will be a histogram at every pixel location within the object, and the bin values represent the brightness of the caustic shadow. So where does this histogram come from? Well, we can apply our refractive deformation G, that is, a 2D warping to simulate the light redistribution process. The deformation field maps the background pixels to the pixels within the object silhouette. And the histogram bin can then tabulate the number of pixels fall within the silhouette. After we compute the histogram, we apply nonlinear mapping to make the histogram values fall within the processing range, in our case, 0 to 255. Then we can adjust the contrast to achieve vector effects. After that, we apply our affine transform to make the caustic shadow. We can apply different affine transform to change the shape of the caustic shadow for different effects. Effect of scene depth can be easily obtained. We can scale the parameter G to make the object appear closer to the background like this. Or we can scale all the components, which is equivalent to scale the whole object. Here, we try to simulate the elephant moving towards the background. As you can see, when the elephant moves closer to the background, it appears smaller. Compound composite can be obtained easily by changing the light transformation in a serial fashion. For example, after the blue object composite with the background, the composite will become a new background for the orange object. So now I would like to show you some results of our approach. The input image for the elephant. This is the markup for the object silhouette M, the tri-map, the markup for the color attenuation beta, and the markup for the refractive deformation G. The R model with the caustic, and the composite result. The fish input image, the markup for the object silhouette, the tri-map for the foreground contribution alpha, markup for color attenuation beta, and the markup for the refractive deformation G. So again, the R model with the caustic shadow, and the composite result. So the lion now stands on the grassland, dragon standing on a walk, swan in front of flowers, chandelier in a new living room, and the dolphin in front of a cat. Here are some results for compound composite. We can change the hue of the transparent object, as you can see for the purple dolphin. We can also scale the fish to simulate scene depth. Here, the swan is in front of both objects. Whenever they move, the appearance of the swan is also changed. The amounts of user interaction and processing time from some of the examples are shown here. So the actual interaction is included in the supplemental material, and more information can be found in the paper. In this chart, you can see beta is the dominant computation, but it only requires to compute once. And G requires the most user interaction, but it can be estimated instantaneously. We evaluate our results qualitatively with composite from Photoshop and ground truth images taken by a camera. Since we are not aware of any tools for mapping transparent objects from a single image, we compare our results with Photoshop. We hire a veteran Photoshop artist to create a composite. we found that using Photoshop requires much longer time. And the composites have no semantic meaning, in contrary to our ARM model. And their composite results cannot adapt to a new background. Our composite is also more preferable from the user study. We also compare our composite against ground truth. So objects with various complexity are tested. And in general, user cannot find significant difference between the ground truth and our ARM composite. So the detail of the user study and other images used in this experiment can be found in the papers. So in summary, we introduce a practical approach to solve a very difficult problem, the mapping and compositing problem of transparent and refractive objects. Currently, our model can handle transparent objects with smooth color attenuation. For translucent objects, we believe it should be handled by mapping algorithms for opaque objects. And solving multi-colored transparent objects with non-smooth color attenuation and video mapping will be our future direction. So you may visit my webpage to find out more details. Thank you.
Thank you. We have time for questions.
This is great work. I'm Gordon Wettstein from UBC, and we actually had two papers at ICCP this year and ICCV, where we reconstruct transparent objects from a single image using 4D light field background illumination. I believe the interactivity from your approach is a limitation that's based on the diffuse background that you use, right? Whereas, what do you think about, what are your thoughts on using higher dimensional background illumination, such as light field displays?
Are you doing, I cannot hear clear. So you say you are doing transparent object reconstruction from single image?
Single image transparent
Maybe
object
you could
reconstruction.
turn on the light for a minute. It's hard to...
Yeah, I cannot hear.
So single
Can
image.
you turn on the lights, please?
Yeah, turn on the light, maybe better.
So we do single image reconstruction automatically of transparent objects, refractive objects. But instead of using diffuse background, we're using a 4D light field background, which gives you more information. More information can be encoded in the background. It doesn't handle colored objects like your approach. But do you have any thoughts on using higher dimensional background illumination than just diffuse objects?
Actually, for this work, our target is on transparent objects, like from single image. So the examples I use here, I just casually grab from Flickr or Google. So our approach is more like a photo editing approach, which normal user can casually download the photo and then they can take it out and then put it on the new background. So I think your taking more information is a good way to for example, doing reconstruction. Actually, we also have our reconstruction paper from single view but using multiple images at CVPR this year. And we do dense photometric stereo. Yeah, you can check out the reconstruction paper in my website too. Yeah.
So you don't use controlled studio illumination?
Yeah, no, we don't have any something on the background.
Great.
Just as, yeah.
I have a small question. So basically, you are using two curves to define the deformation.
The reflective deformation.
Yes. So I'm wondering, have you thought about, is it possible to define any type of deformation using this way, or is it, what are the classes of types of deformation?
Actually, because we use frame plane spline, so the deformation, the model is by the frame plane spline model. So of course you can use different deformation model. As long as you can specify pair of strokes, then you can generate the effect that you want.
Yeah, but I'm asking the reverse. So if you have a real reflective object, can you model the reflectiveness using these two?
The real reflective, so actually what we do is we take an image of the real object, we compare the ground truth, and then we do use our method to try to simulate the real reflective deformation. And actually, interestingly, we perform a user study, we do the pairwise force choice approach, something like that, and the user cannot find significant difference. And I think it explains, because our human visual system, very interesting. Because when a transparent object, if you don't have reflective deformation, you will think there's something wrong. But when there is a reflective deformation, you cannot tell it's true or not. Yeah, I think it's the reason. Yeah. Thank you.
So that's thank you again.